Figure 2 shows a sketch of part of the curve C with parametric equations. These. The curve crosses the y-axis at the point A and crosses the x-axis at the point B. Show that A has coordinates 0, 3. Find the x-coordinate of the point B. Find an equation of the normal to C at the point A. And the region R, shown and shaded in figure 2, is bounded by the curve C, the line x equals -1, and the x-axis. Use integration to find the exact area of R. So that's the question then. Got it summarized here. So show that A is 0, 3. So I'll just do that here to save some space. So here x is equal to 1 minus a half t equals 0. So putting in the 0 value for x, aren't we? And that must be, t must be 2, mustn't it? We can read that off straight away. So y is equal to 2 to the 2 minus 1. 4 minus 1 is 3. In other words, A has coordinates 0, 3. So there's part A. Find the x-coordinate of B. So part B then. So here, x-coordinate of B, well this would be when y is 0. So 2 to the t minus 1 equals 0. 2 to the t is equal to 1. Clearly anything to the power 0 is 1, so this tells us t is 0. So when t is 0, we get y is 0 of course, and t is 0 here, that's 0, x equals 1. So we found the x-coordinate of B there. So B has coordinates, I've put them in 1, 0 and 0, 3. I've put them in the diagram already. Find the normal now to C at A. So C. So dx dt, we need dx dt and dy dt, don't we? Because we need to get dy dx first of all. So dx dt is, differentiate this goes to 0. This is minus a half, isn't it? T goes to 1. So it's minus half lots of 1, which is minus a half. Now y is equal to 2 to the t minus 1, which we can write as e to the t ln 2, isn't it? Because if you think about it, that would be 2 to the t when you bring the t up, and e and the log disappear because they cancel each other out, and you're left with 2 to the t. So you can write this for derivative purposes as this minus 1. This is easier to integrate because it's e to the so many t's now, which is a function of a function. So dy dt then, use the function of a function rule, e to the something t. E to the something differentiates to e to the something. So that's t times ln 2 multiplied by the something differentiated, and this something differentiates just to ln 2. The constant goes to 0. So dx dt and dy dt, which I should have written there, shouldn't I? Put it in, is equal to this. So dy dx then. So dy dx is equal to dy dt. So e to the t times ln 2 times ln 2 divided by dx dt, which is minus a half. So that's equal to minus, the 2 can swing up. We can bring the ln 2 to this side, make it look easier on the eye, and also e to the log n 2 lots of t. We can write like this, can't we? That's easier on the eye. Okay, so there's that then. So there's dy dx. Now at A, which is 0 and 3, dy dx then. When x is 0 at A, what was it? Did we say in parts? T is 2 at A. T equals 2, so dy dx then is minus 2 ln 2 e to the 2 lots of log 2. So I'll write it this way round. Okay, so there's dy dx then is equal to that. So normal, so equation of normal. At a, 0.3 is y minus 3 is equal to m, the gradient of the normal. This is the gradient of the tangent. Oh, which we can simplify. Minus 2 ln 2. This would be 2 squared, so it's log 4. E to log 4 is just 4. So that's equal to minus 8 ln 2. So our gradient of the normal then will be 1 over 8 ln 2 times x minus 0. So that tells us that y is equal to 1 over 8 ln 2 x. Then move the 3 over to be plus 3. Y equals mx plus c. So there's the gradient, the equation of the normal. Okay, so that was part C. Now we can look at part D now. Use integration to find R exactly. So the region R is equal to the integral between minus 1 and 1, wasn't it, of y dx. Let's just go back to the picture so that we're happy with this. Minus 1 to 1 of integral y dx. Y is 2 to the t minus 1. So that's equal to the integral minus 1 and 1 of 2 to the t minus 1, now dx. Well, we know what dx dt is, we've done it already. Dx will equal minus a half dt times minus 1 half dt. Now we go from x equals minus 1. So what does y equal? That was 1 minus 2t, wasn't it? So t would need to equal, let's have a look here. X, where's x? Quick look. 1 minus a half t rather. Put that in. 1 minus a half t equals, so therefore the half t, move it over to this side, will equal 2. So that tells us that t equals 4. And x equals 1 equals 1 minus a half t. Clearly t would be 0 here. So we've got on these values and here, we've got from minus 1 it was t equals 4, and to 1 it was t equals 0. So that's equal to then, we can flip the integral around the other way and drop the minus and just write this around the other way if we want. 0 to 4 of 2 to the t minus 1 dt. Put this in a bracket, and now we'll find out what r equals. So r is equal to then a half. Now let's do the integration. Now again we're going to write this in the form that is easier on the eye. E to the log of 2 to the t, and the t can come down here. Yeah? So that's how we can write that. Minus 1. Now we can integrate e to the at. It's a half. This was between 0 and 4. Okay, e to the at, this is the a value, is e to the at. E to the t ln 2 over the a, which is log 2, isn't it? That's the integral. Minus, this integrates to t, and we need to work this out between 0 and 4. So that's equal to a half. Top value, take bottom value. Top value, put 4 in. E to the 4 log 2 is e to the log 16. 2 to the 4 is 16, which is just 16 over ln 2. Put 4 in here, minus 4. And then put 0 in. E to the 0 is 1. 1 over ln 2 minus 0. So that looks like what we get. So we get 16 minus 1 is 15 log 2. 15 over 2 log 2 then. minus, and there's a 4 here over 2. So it's minus 2.